Ceph is a shorthand for cephalopod, which is a family of octopuses, squids, and so on and so on. And like every other animal, it needs some handling, some taking care of, and we had a lot of issues in the past. We are expecting to have another lot of issues, and today I'm going to speak about what we have experienced in the past and how we handled it, so the customers would release. One of the important issues we had in the past was the scanning issues. So let's assume we have a big 4 petabyte cluster. So everything seems to work fine as long as everything works fine. Customers are happy, they have access to their data, and so on and so on. But we have a problem. We might have a problem like months for some reason go out of the quorum and new clients cannot connect, or there are performance issues so severe that customers can't access their data, or data access is very slow. So we had these problems in the past, so we decided to fix this for the customers because we cannot afford this. This is not only a problem for us, but also for customers who might don't like it, so they will go to competitors, so they will try to sue us, and so on and so on. So they are generally unhappy. So we had to do something, and the first thing we came up with is to downscale things a bit, and instead of having one 4 petabyte cluster, we divided this in 4, and now we have 4 1 petabyte clusters. What does it change? When we have similar issues, it's affecting only limited number of customers. So we still have unhappy customers who are going to sue us, go to competitors, and so on and so on. But at least the number of these customers is limited. There are other issues as well. For example, here, let's assume that we have a 4 petabyte cluster filled in 60% with data, and with a replica factor of 3. So we have nearly petabyte per replica. Now, let's assume that 2/3 of the replica fails for whatever reason. The actual reason is not important at this point, but let's assume this happened. Ceph will handle this, of course. It's not a problem for him, but the problem is that there is a 540 terabytes of data to recover, which is a lot, and it will take a lot of time, and will degrade performance for many users, and this is going to hurt. But if we are going to downscale this to 1 petabyte, in the same scenario, exactly same scenario, we have only 135 terabytes to recover, which is a lot less, and can be done in a reasonable amount of time. This fixes a lot of other issues, like rolling upgrades, which can go wrong for whatever reason, data center issues, and so on and so on. Also, human errors and rogue users. Rogue users don't need to know they are rogue. There are many reasons why they are rogue. For example, they are issuing deep flattened images of a lot of images, so this is going to hurt a lot because the deep flatten is costly operation, so the performance for everyone is going to degrade. Or they are doing a lot of clones and then they are removing it. This is also costly in terms of performance for the cluster, for the user. So if we are going to downscale this, we have still the same problem, but on a smaller scale, because it is affecting only one cluster and not every customer. And speaking of rogue users, we had an issue with latency spikes. We had latency spikes exactly 5 minutes, which, as you can see, is exactly something that looks like a cron job. So it cannot cannot go this way. So we started digging. We started asking around. Is this your cron job? Did you set this cron job? No, nobody knows anything. So we had unfortunately to dig further because these latency spikes are simply unacceptable for us, and it started to affect customers. What you can do at this point? We increased logging everywhere, so we could minimize the number of affected OSDs. Then we gathered the intelligence that way. Now we had hot OSDs. Then we increased logging of those OSDs even further, and then we collected needed data. In our use case, which is RBD images, we increased the debug object class to 20, which is usually safe to do because object class doesn't log much, usually. Then you can use Greylog or similar log gathering tool to pinpoint affected OSDs. On the screen you can see that Greylog can show you which OSDs are showing unusual activity due to increased debug object class. Now, on the screen you can see that we have the add child and remove child operations repeating every 5 minutes. And what is important here to note is that we have two different images in play. So this means that we have not one but two monitoring tools. In this log line you can also see the image ID, which tells you which image it is, and you can convert this to image name. Now that we have the hot OSDs, we can increase logging on those OSDs to more interesting level, but you need to be careful. What we need to find is the IPs of the customers or clients which are making us trouble. So we had to increase debug OSD to 10. But remember that this kills performance, so use caution and remember to revert this once you are done with this. Now we have collected the data. We know the IP address of the client affecting us, what kind of client this is, which is in this case OpenStack Cinder, and something that confirms that's affecting us, which is add child, which tells us this is cloning of the image. So we took those IPs, we searched out our databases, and we found out that these were two guys who were previously telling us that they don't have anything to do with this. So case solved, but it's not the end of the story, because it turns out that this was the reason for unexplained disk space increase. Within 3 months, we jumped from the nearly 55% to 75%, which is close to be deadly for the Ceph cluster. And we had little time to find out what's going on. We already know it can be caused by adding clones and removing clones, but we had no exact evidence. So we started digging again, and interesting thing here is that the Ceph was reporting different space usage than operating system. So we started digging deep in the Ceph internals, and we realized that information for the Ceph PG query returns something out in the field snapTrimQ, which means probably that Ceph doesn't keep up with snap trimming. The first thing we did was to increase the snap trim frequency and concurrency by issuing these commands: Ceph OSD inject args, OSD PG max concurrent snap trims, and OSD peak snap trim sleep. You can do this at runtime, and voila, we revert to the trend. Now, why this happened? When you are issuing a snap array, you are in fact not removing snap right away. What you are doing is you are telling cluster that you want this snapshot to be removed. In fact, once the Ceph cluster receives this command, it queues the snapshot to be removed, and then it is removed at its own pace, which is also set by snap trim queue frequency. And when we have this case of snaps and clones removed every 5 minutes, we have trouble because suddenly Ceph doesn't keep up with removing snaps. This could have been prevented if we know that we have to monitor, but we even didn't know how to monitor this. So what we did is we issued a pull request to make this issue more visible, and thanks to this pull request, when the snapstream queue goes way over the limit, it goes simply health warning, so it will give you the signs that you have to act right away because there is something wrong. Probably you are removing and adding snapshots too fast and you are in trouble. So you have to act, really. This pull request also improves integration with monitoring because you don't need to parse snap trim queue any field anymore. It's just a simple integer which you can put into any monitoring tool to graph it or put it into Gauge or whatever you want. This was merged in master and was backported to Luminous, but unfortunately full backport to Jewel is not possible, so if you need this feature, you will have to upgrade, unfortunately. Another interesting story is with broken RBD children. So, we are using mostly RBD images, and we are using them to host VMs, virtual machines, so we are setting them up in no time. So we have 2 pools and 2 users. User A, administrative user, which manages the pool A, which contains original parent images. And we have user B, which manages clones of those images, and has full rights to pool B, which contain clones, but doesn't have access to the pool A. Now, this raises one issue because once user B removes the clone, there is a issue with access. Because user B can't write to pool A, it cannot break the bidirectional link between clone and parent image. And this is important because if it cannot remove this link, we are getting in trouble. So let's assume that this clone was removed and administrator for some reason issues the command RBD children. The Ceph panics. It tells us that the image doesn't exist, which is weird. And this is a reason to panic because suddenly we have a data loss situation. In fact, it's not true. When you increase login to display some more diagnostic data, we are seeing that there is an error looking up name for the image ID. So how do we fix this? To fix this, we have to understand how this works internally in Ceph. So Ceph RBD actually maintains something called RBD children object, which contains the OMAP database, which consists of key and value, which is formatted as a key containing parent and snap information, and value containing information of clones. What we have to do in this case is to remove offending clone from this OMAP. Sounds simple. It's not. It's not because this is binary data, and you need to know how it is formatted and how to modify this data without destroying your RBD children object and doing even more damage. So for particular key, there is one value, and value consists of number of children, children ID length, then children ID, and we need to decrease the children count and remove offending ID. When you are looking at this information, which is taken directly from the Ceph code, you realize that you have to decrease the field clone count and find the offending clone ID field, and of course the ID length. In the key, you have information about parent pool ID, which is ID of the pool containing parent image, and there is also length of ID, actual ID of the parent image, and then ID of the snapshot. So as you can see, there is no easy solution to fix this. And instead of doing it by hand, we wrote our own tool. We haven't published it yet, but we are planning to do so in some future. Unfortunately, we stumbled upon the problem writing it because, as you saw, the key and value contain null chars, which LibreAdos doesn't accept. It stops at first null char, which means we are in trouble when we want to manage those keys and values for the RBD children. There's simply no easy way to do this using plain LibreAdos, and we had to be creative in using object class to access those data and modify them. But we did it. Anyway, we extended the LibreAdos C API, and we are expecting to have this merge sometime in the future. Again, don't try to fix this manually because you can break even more. And if you are already in this situation, don't hesitate to ask us for help. We can help you out. And better yet, don't let this happen to you because it's a tricky situation, and if you are caught with this in the middle of the night, you might be in even more trouble than you wish. So also an option is to upgrade to Dual or newer version because as far as I'm aware, there are fixes for this in these versions. Okay, so do you have any questions yet? Yes?
Yeah. So if I understand well your first point, the scaling issues, you had to basically break down a big cluster into smaller clusters. In your experience, can you tell us what is the size that would be comfortable for you to handle? Like, obviously you can do very big clusters, but what is like the most comfortable size of a cluster that you can do?
Well, this mostly depends on your usage, because if you have many clients, many customers using this cluster, you might want to go with something that's the best balance between performance and capacity, which in our case we are simply betting for like half petabyte, and if this is needed, we are increasing it to 1 petabyte at most.
Okay, thank you.
And anyone else? Okay, thank you.
Okay, so I have still a few minutes left, so I have a bonus for you, which is don't use broken tools. Actually, this is not our story, but I'm going to share this so you're aware. On Ceph users mailing list, there was a message stating that someone was complaining about increased disk space usage on their cluster, but it wasn't the case we faced. So after some time, they confessed what's the issue. The issue was the collective plugin, which was invoking the Rados bench every minute, and sometimes this plugin didn't finish, so it was leaving trash data in their main production pool. So this alone is quite problematic, but I will show you why this is even more problematic than it sounds. The core of the plugin is this comment, which you can see here, and there are way better ways to do this. So what's the problem? First problem is that they are invoking the write test on one thread, performed for 10 seconds, and on block size of 64 kilobytes. This has little relation to the reality in most cases, because in our case, for example, we are dealing mostly with 4 kilobyte IOPS and 4 megabytes IOPS. And this is mostly when we are doing recovery or some other stuff like that. Another issue is that it performs writes. And what if your workload is mostly read? It doesn't account for this. And in case of Ceph, writes are always slower than reads, and you have different data. Again, no relation to your reality. Finally, as the final nail to the coffin, there is a timeout 30s, which can be problematic for many reasons, like, for example, the cluster writes so many objects so fast that it happened to not erase them in the remaining 20 seconds. It happens. It can happen and will probably happen. Or simply, the primary for the objects written can die in the middle of the test and it cannot go away. So it hangs, timeout kills it, and the trash objects remain. What you can do instead is to issue the Ceph daemon perf dump on any interesting OSD daemon and collect the data. And if you need the latency in milliseconds, you could divide the delta of sum and average count fields and multiply that by 1000. I'm talking about the delta because this is total accumulated numbers across entire Ceph lifetime. So you should take a value at one point of time, then at second point of time, calculate the difference between them, and then use that in your equation. And this will give you the latency in milliseconds. And if you are in this mess already, you have trash objects, you can always clean this with the radius cleanup command, and also you need to provide the prefix benchmark data. This will clean the benchmark objects without affecting anything else. So you don't need to copy the pool, you don't need to hack some weird stuff around. You just issue this and you are done. Okay, so this is everything from my side. Feel free to follow me on Twitter, on GitHub, connect on LinkedIn, and also feel free to visit my website. Thank you.